Hello, students, and welcome back to some more linear regression adventures. In this video, we cover the topic of potential issues with linear regression. The idea here is that when we fit linear regression models, we are assuming lots of things. We're making strong assumptions about the data. If those assumptions are incorrect or more than a little bit incorrect, substantially incorrect, then the results from our models, inference, prediction will be quite dubious. Um, Specifically, if you recall, in linear regression, we assume, well, many things. We assume that the relationships between the predictors and the response are linear. Relationship here because, of course, we can have several predictors. Linear and additive. Well, yes, we simply, to describe why, we simply add the effects of each of the x's, beta 1 x1 plus beta 2 x2 plus blah, blah, blah. Um, Other things we assume the errors have a mean of 0 and do not depend on the predictors. Errors are homoscedastic. That's a fancy word that means constant variance. So homoscedastic constant variance. And especially their variance does not depend on the predictors. So regardless of what x values are, the errors should always have the same variance. Errors are uncorrelated, uh, and also in the case of the strong assumptions, and recall we need the strong assumptions to basically for inference, meaning to compute confidence intervals, to conduct statistical tests. Well, under those strong assumptions, the strong assumptions say that the error should be normal, which is pretty strong or restrictive assumption to make. And so, in reality, to make sure that linear regression is applicable, is appropriate for your data, and to make sure you can correctly interpret the outputs from your models, you need to have some level of confidence that those assumptions are met or approximately met. Now, here a little example. Actually, it's an example from before. It was called example 6. Where you had data that was strongly not linear in the sense that y was a function of x squared. In which case, if you were to fit y equals beta 0 plus beta 1 x only, well, you will get a pretty bad model. Now, we already saw this. You could already see this when you plotted y against x. So, if you plotted y against x, as before, you will get something like this. Okay, and here the noise in this example was very small, so all the points were very closely following the function here, because again, this error term has a very small variance. And so you see, this is not linear in the sense that if you fit a straight line to this data, you'll get something like this. Okay, that would be your best line of fit if you follow linear regression. Okay, so already if you look at that, you will know that. You will know if this is y, of course, and this is xi. You will know that this is not really appropriate. Another way to see this is actually to plot the residuals of your model against the x values. And if when you do that, you see a pattern, you see some sort of shape that is not just a cloud of points, then you have indication that your model is not appropriate. In this case, the linear assumption is not correct. And here, if you think about it, when you plot the residuals against the x values, you see such a strong trend here. It's by far not a cloud of points, which makes sense because here, those residuals, they start positive. Well, yes, if x is small, so if we're here, the residuals are all positive because, well, the fitted value, the real value minus the fitted value is positive. Recall, what we call residuals here is simply the actual values, the actual y's minus their predicted value, and the predicted value would be the value of y on the straight line. So yes, for small values of x, all those quantities are positive because the blue line, I mean, where the points are is above your prediction. Now, there's a whole segment of points for which now your prediction is above the actual values. So the prediction is higher than actual values. This quantity will be negative, and indeed here we are in the negatives for the residuals. And lastly, the last segment, we're back to having the actual values bigger than the prediction. So we're back to having residuals that are positive. Okay, so here again, you see a very strong patterns between the residuals and the x values. That's an indication of the linearity assumption is not met. Now, here, this is an outline, so a bit more systematically, we're going to cover a few potential issues. They're not going to be issues every single time every single time you try linear regression, but those are things you should check to make sure that linear regression is appropriate for your data. So non-linearity, correlation of the error terms, non-constant variance of the error terms, potentially outliers, potentially high leverage points. We're going to explain what high leverage means, collinearity, and lastly, confounding effect. I suppose confounding effect is can be true in general, but it's the idea that even if you have significance or predictors are strongly correlated with your response, well, correlation does not imply causality, something you probably heard before. Okay, so now let's jump into the first point, nonlinearity. Basically, we just discussed this here. Here, in this example, we plotted the residuals against the one and only predictor, which makes sense if there's only one predictor. And you can detect nonlinearity like that. In general, or more generally, what you do is you'll plot residuals versus fitted values. Because in general, you might have several predictors. So then, yes, you can plot the residuals against x1, but you need to do this with x2, with x3, blah, blah. So it's a more, let's say, compact way to assess this is to plot residuals against fitted values. Fitted values, of course, the y hats. But the idea is essentially the same. You should not see any patterns there. If you see strong patterns, if this is anything else than a cloud of points, well, it means something is off. Your model is not properly specified, and potentially you have non-linearity there. For example, here in this example, it's an example from the book. So we're fitting MPG versus horsepower for different cars, I believe. And here, yes, there is a pattern. It seems like at first, when fitted value increases, the residuals are decreasing on average, and then eventually, maybe here they're kind of average, but then they increase. So yes, here this is not great to see. Now, as a note here, there's, at least for this data set, a pretty simple fix. If you simply add a quadratic term in your regression, so if you simply model y to be, well, you can have an intercept, you keep the linear term, so you keep the x, but then you add simply x1, the same x, maybe here we can just call it x, but squared, it's going to solve basically this problem. Essentially, there's no more patterns between the residuals and the fitted value. This looks more really like a cloud of points with no strong trend. Okay, so here, the quadratic model, and by quadratic models, we simply mean this. You add the x squared term here, removes much of the pattern between the residuals and the fitted value. Okay, another potential problem is correlation between the errors. So yes, in essence, we make the assumption that the correlation, or equivalently the covariance, between any of the errors, this should be zero. That's an assumption of our linear regression model. Okay, if I is not equal to j, of course. Now, how can we check this? Well, that's a very simple way. Not sure it's the best way, to be entirely honest, but let's still explain what is presented there. Here we are simply plotting the residuals. Just ordered. Okay, so this would be the first residual, the second residual, and so on. Okay, so in essence, we cannot see any sort of trends here. This is an example where the actual correlation between the residuals is zero. So this is verified. And here we don't see specific trends, meaning this residual is the first residual is here, then the second is here, here, but then you go down, then you go up, then you go down, and then you go up, then you go down. Okay, so it seems pretty random the way those residuals are, not over time, but as a function of just their order in the data set. But now, if you compare this to an example where the correlation between two consecutive residuals, so this should be the correlation. So the correlation between epsilon I and epsilon I plus 1 is actually quite high, 0.9. And here you will see patterns in the sense that if a residual tends to be high, okay, above its long-term average of 0, well, it tends to be followed by another residual which tends to be above 0. And then here, same thing. The next one tends to be 0, the next one tends to be 0. Then eventually, okay, there's still randomness, right? This is not a correlation of 1. So then, okay, this one goes down. But then once the residual are below their mean of 0, they tend to stay below their mean for a while. Then they go up, and then they tend to stay up for a while. Okay, and then they go down, they tend to stay down for a while. You see, this is as opposed to the pattern here where it was more or less always changing up, down, up, down, up, down. Okay, so if you plot the residuals, the ordered residual here, and you see trends like that, okay, that might be a sign that it is a sign that there is correlation in the error terms. I said it's not the best way, in my opinion. Well, it's not so easy to the naked eye to see that. And when the correlation is 0.5, yeah, you will see some patterns, but they're not as clear. What you can do instead, in my opinion, is just compute this thing. Okay, compute what is often called the autocorrelation between the residuals, and then if you see things that are values that are big, like 0.9 or 0.8, well, then you will have an indication, right? So you can actually compute the correlation between sequence of residuals. But I suppose take this more as a comment because we don't present the details here. Okay, third potential problem, non-constant, well, here this should be variance of the error terms. Okay, non-constant variance of the error terms. And this is, you can detect this visually with the same plot as before. Simply plot the residuals against the fitted values. And if you see not really a trend in the sense that it's increasing or decreasing or going down and up like we had before, but simply that the variance seems to be increasing or decreasing as the fitted values increase or decrease, well, this is an indication that you are violating the assumption of constant variance for the residuals. Because again, the assumption is that variance of the error terms, well, this should be a constant. Yeah, it should not. The error should not be bigger or smaller, or their variance should not be bigger or smaller as function of the fitted values. So here, this would be a case that yes, it does seem that initially the variance is small. The residual vary well, they still vary. The variance is not 0, but they don't vary nearly as much as when the fitted values are large. And here, I mean, it's not always going to be a fix, but a kind of quick fix that is used quite a lot in practice is to make the following transformation. So instead of fitting y against the predictors, you're going to fit ln. Okay, well, here they call this log, but I'm pretty sure they mean the natural logarithm of the responses. And you have basically a linear regression model, not for y, but for ln of y. And if you do that, often it has the effect of substantially decreasing the non-constants of the variance in the errors. I mean, not necessarily, but in this specific example, yes, it does. It does seem that yes, that there's way less variability in the variability of the residuals as a function of the fitted values. Now, an important downside, I would say, of those kinds of models is that they're harder to interpret then, because now you're not modeling y, you're modeling ln of y. So the interpretation of the coefficients here is not as straightforward. Outliers. Okay, outliers. And by the way, here, each of those topics could be a much bigger topic. We could spend literally hours discussing all of those things. I suppose it's a bit of an introduction here, so we want to make you aware of those things. You should check those things. Okay, you should definitely do those plots when you do linear regression practice, and hopefully you don't see any patterns. But if you do, it means you need to change something in your model. Outliers. At least qualitatively, what an outlier means is simply this: it's a point for which the response y is far from its predicted value. Said otherwise, it has a large residuals. Well, yes, if the distance between yi and its predicted value is large, well, this is what we said here. Y is far from its predicted value. So an example here, in this linear regression of y against x, most points are pretty well, pretty linear. They form a pretty strong linear relationship. There is one point that is far away from the fitted line, and is this point, point number 20, apparently. You see it's an outlier because its y value is very far from what is predicted by the model. And here, for your information, um, the yes, the red line is the line fitted with this observation, and the blue dashed line is the lines fitted without this observation. And frankly, there's not much difference between those two. So here, this, I suppose, makes the point that it's not because a point is an outlier that it necessarily has a huge effect on the model. So outlier, at least for our purposes, simply means that uh, it's a point for which the predicted value is far from the actual value, the y values. Okay, this essentially presents the same thing. The residual here is much larger for observation 20 than for essentially all the other observations. And lastly, this last plot on the right is something called the studentized residual. To interpret the residuals, it's better to look at the studentized residuals because they are essentially, I don't want to call them standardized residuals because standardized residual has slightly different meaning, but you can view it essentially as a residual that has been divided by an estimate of the standard error of the residual. So yes, in some sense, it's a standardized residual, which helps interpretation because this is a rule of thumb, but the rule of thumb is if the studentized residual is bigger than 3 or smaller than -3, then you will say you have an outlier. So again, we don't present the exact mathematical details here, but you can view the studentized residuals for our purposes will be the residual divided by an estimate of the standard error of said residual. Okay, and so this thing rigorously under the strong assumptions would have a student distribution. That's probably why it's called the studentized residuals. And then in which case, if this is bigger than 3, the rule of thumb is it would be considered very big, meaning you have an outlier. The residual is bigger than expected by the model. Okay, this in absolute value should be bigger than 3. And in this case, yes, the studentized residual is huge. It's around 6. So yes, you have some sort of confirmation that you have an outlier here. Now, this is outliers. Again, points for which the y value is far from the predicted value. We have the perhaps related but different notion of high leverage point. Now, a high leverage point is a point that has an unusual value of their predictors, okay? Not necessarily of their response, y. So what does that mean? We have two examples here. So, okay, first we look at again our data of simply a single y against a single x. So it's the same data as before, same data as here, but we've added a point that is now a high leverage point because this point here, the point number 20, is not a high leverage point because its value for x is not unusual. It's kind of in the middle of all the possible x's, so it's not unusual at all. If we add this point number 41, this is now a point that has an unusual x value. Well, yes, because its x value is bigger and actually substantially bigger than all other x's. You see, all the other points, their range for x goes from roughly -2 point something up to 3. And this one has a value of x of 4. So it's actually substantially bigger than the next biggest point in terms of x value. So yes, it's an unusual x observation. And here, I suppose the point is that a high leverage point has the potential to strongly impact the fitted line. your fitted model, basically, right? And this is actually happening in this picture. You see, same thing. The red line is fitted with this point in the data set, and without this point, we would have the blue line. So you see, there's a quite substantial difference between the red line and the blue line. And yes, this point, because it has a high leverage and it's relatively far, its y value is relatively far from what is predicted by the blue line. It really shifts the fitted line towards itself. You see, this point, because it has a high leverage, it is shifting the blue line to come closer to it. It is really changing the slope and intercept of the fitted line. Which was not the case for the point number 20. You see, this was an outlier that didn't have such a strong impact on the model, because it did not have a high leverage, because its value for x was typical. And here, this is just, I suppose, this plot. I view the utility of this plot just to show you the following. This is an example where, imagine you have two predictors, x1 and x2. Now, this point here would be a high leverage point, even though its value for x1 is not atypical. You see, its value of x1 is around 1, and there's plenty of points here that have a value of x1 around 1. Likewise, its value of x2 is around -1, and you see, there's plenty of points here that have values of x2 around -1. So individually, it's not atypical in its x1 value, and it's not atypical in its x2 value, yet this specific combination of x1 and x2 is atypical. So this point here, if you had two predictors, would be a high leverage point, most likely. Again, because its value of the predictors is unusual. And then what's happening here on the last plot, we're plotting the leverage. We're going to explain how can we give a numerical value to measure the leverage, but we're measuring the leverage of all the plots. All the points. I suppose those are the points in this first example here. The leverage bit, the scatter plot, of the leverage against the studentized residual, and what we're highlighting here is that point 20. Even though the studentized residual was huge, so it is an outlier, it doesn't have a specifically large value for the leverage. So it's not a high leverage point. Point 41, however, has a very high leverage and also a pretty high value of the studentized residual, around 3. So here, arguably 41 is also an outlier. So it's both a high leverage point and an outlier. Okay, so how do we judge numerically if a point is a high leverage point? Well, using this thing. Now, first bullet point is repeating what I said. High leverage points are of concern because they have the potential to significantly affect the estimated regression line. And here we really mean potential. It's not all the high leverage point. Sorry, it's not all the high leverage points that will influence a lot your regression model, but they have the potential to influence your line, your fitted line. Now, how do we measure the leverage? In fact, there's several approaches, but a relatively simple one is using this so-called hat matrix. So this is the hat matrix. By the way, this last X was not put in bold by the careless lecturer that I am, but it should be bold here. Okay, sorry about that. It's the same X as usual, the design matrix. Okay, now you create the hat matrix in the following manner. And then you obtain the leverage by simply computing the diagonal entries of this matrix. So here, little HII would be the entry on the row number I and column number I of this matrix. Okay, this is a square matrix to compute all the dimensions. And it is it is the leverage of observation I. Now, I think a relatively neat way to view why this measures the leverage is this decomposition here. Now we don't show the proof, but you can show that any fitted value, so any y hat I, can be written as, in essence, a linear combination of all the responses. Okay, so those yj, they don't have a hat, so they're the actual observations from the y. And each of them has a certain weight, and the weights are exactly those given by the hat matrix. So hij is the entry in the on the row I and the column j of the hat matrix here. And you do the sum, you sum for all the observations. So your sum goes or runs from j equals 1 to j equals n. Now, if you rewrite that, you can write the first term here to be hii yi, and then all the others. But this term, you see, is the hii that I told you is some measure of leverage. But this hii, what is it when you write it like that? It is the weight of observation I on its own prediction. Okay, the weight of observation I on its own prediction. If this weight is high, it means that this observation has the potential to influence a lot the regression model because it has a huge weight on itself. So it's influencing is its own prediction a lot. Hence, yes, it is an observation that can really change the regression line quite a lot. At least partly because it can influence its own prediction a lot. Now here there's a rule of thumb, and the rule of thumb is if hii is bigger than this thing, 2p plus 1 divided by n, then we say it's a point with high leverage. And just to make sure I make sense when I say that it has the potential to influence the regression line, but it doesn't necessarily influence the regression line. Well, just imagine here that this point wasn't here. Imagine that it was here. Well, in which case, it would have been exactly on the predicted line without the point, and it would not have influenced the point at all, right? But we're just saying if it has a typical value for the x, it's a high leverage point, and a y that is away from the regression line without itself, then it's going to strongly shift the regression line towards itself. And the explanation here, I suppose, is that, well, remember that the regression is minimizing the square of the errors, but this point has a huge error here. So, and this error squared, okay, the residual, so the error squared, or residual squared, will be huge. Will be huge if you keep the blue line. Now you can reduce this term substantially if you shift the line like this, because yes, then this error will be diminished quite a lot. Okay, so yes, this point will really shift the line quite a lot in order to diminish one single error. Okay, here an example of the same concept. Yeah, so similar example actually. So here we okay, so revisiting example 1 from before, where you have a linear regression model, but now here we're gonna add to this data set. So this is the original data set. We add a high leverage point. So we add basically this point here, which obviously is a high leverage point because its x value is very far from all the others. And here this would be an example where there's high leverage, but it's not really an outlier. So yeah, the leverage is high because when you compute, when you compute HII for this specific point, and you compute this sort of reference here, 2p plus, well, p here is just 1, so you would have here, this would be 4 divided by 31. Okay, the leverage is much higher than our bound. So yes, you conclude it's a high leverage point, which you kind of already knew from the picture. I say it's not an outlier because, sorry, it's not presented here, but the residual is not that huge. I mean, it's not small, but if you compute the studentized residual, it's going to be substantially smaller than 3 here. Because, and I mean, visually you can view this. So predicted line with the leverage point is the orange one. So the residual would be the distance between the orange line and this and the y value cross point. Okay, it's not small, but it's somehow similar to other, okay, to the residuals of other points, and they're not the studentized residual are not bigger than 3. Yeah, I believe that's all there is here on points. I had picked up a typo before. Yes, sorry about that. So here, this sentence is not, this word is not correct. So if HII is bigger than this, the predictor can be considered a high leverage. It's not the predictor. So sorry about that. It's not the predictor. It's the point, basically. The point. The point I is the one with the high leverage. The concept of high leverage applies to individual points. Yeah, maybe there's an equivalent concept for predictors. I'm not too sure. But I'll just say it's outside the scope of the lecture today to save myself. Okay, point number 6, collinearity. So let's review what this says. 2 or more predictors are closely related to each other. Well, that's the definition of collinearity. So if 2 or more predictors are linearly dependent, said otherwise, there's a high correlation between 2 predictors. This is what it means for the predictors to be collinear. This is an issue. This is an issue because if columns of our design matrix are linearly dependent, the matrix X transpose X is singular. It's non-invertible, so then you cannot solve the equation that we had much before. Okay, let me just find a more efficient way. I should not have done that. We're just going to wait. Okay. Oh, still moving. Bear with me. I just wanted to show you the beta hat formula that uses the inverse. Okay, I'm just going to scroll. Should be faster. Now that I've committed to showing it to you, I need to do it. Otherwise, we've just all wasted time. You might say it's an example of the sunken cost fallacy, but I'm going to commit. I'm going to commit to find the formula for beta hat, which obviously is not there. It should be in the multiple linear regression. I'm just talking to fill the time here and avoid embarrassment. I've missed it, of course. Yeah, so this is the beta, right? So to find the beta hats, the least square estimates of your betas, you need to invert the matrix XTX. But here we're saying if the columns of the design matrix here are linearly dependent, meaning that some of the predictors are extremely correlated with each other, you cannot solve this. The matrix is not invertible, and hence, for estimation, it's a big problem. Okay, going back to where we were. Couple more slides. So yeah, that's a problem. It makes the fitting tricky because it increases the set of plausible coefficients values for beta j. And then it's going to cause, so collinearity causes the standard errors of the betas to be very large. Now, to make this point clear, I think we can present a sort of extreme example. So bear with me for a second. So yeah, let's create an extreme example. Imagine that reality is like this. Y is beta 0 plus, let's make things simple for ourselves. It's going to be just x1, okay, plus x2 plus some error. Okay, so here we're saying, well, beta 1 is 1, beta 2 is 1. Okay, perfectly reasonable linear regression model. But now imagine we have absolute collinearity. So imagine extreme case where x1 equals x2. Well, what happens then? It happens that this model is not unique in the sense that this is completely equivalent to saying that y equals beta 0 plus, then you can have whatever you like. Remember, x1 is the same as x2, so you could say, well, 2x1, right? Plus the same error. Those models are equivalent, again, because x2 equals x1. So in this case, you would have beta 1 equals 2, beta 2 equals 0. But this is also equivalent to saying beta 0, y equals beta 0 plus, say, 3 offs of x1 plus just 1 off of x2 plus epsilon. Meaning, of course, beta 1 is 3 offs, beta 2 is... All those models are identical, but so if you fit actual data from this model, how are you gonna pick the actual betas? There's going to be a huge standard errors on those betas because, in some sense, they're not really clearly determined. Now, what would be the answer in this specific extreme example? Well, pick the simplest model. Just pick this one. Now, if really x1 equals x2, you don't lose any information by removing x2 from the model, and actually you get to a model that's more parsimonious, and this model would be great then. Okay, so yes, when variables are strongly collinear, simple solution, just remove one, and you're not going to lose any information because again, all the information in x1 is also in x2. So if you lose x2 or x1 and you just keep one, you haven't lost any information. Okay, there's another illustration from this in the book, making the point that collinearity makes optimization much harder. Well, this is already, I think, the point that I've made. How are we going to choose when you optimize this case versus this case versus this case? In fact, there's an infinity of cases that make this model equivalent. And the picture they present is here. Yeah, let me try to explain. So this is an example without collinearity, and this is an example where there is collinearity. Now, before I jump into the explanation, let me just take a sip of my Milo beverage here. And yes, I still drink Milo at my age. It's not only for kids. Yeah, it's full of vitamins, and it is delicious. Now, the point here is just to explain that without collinearity, optimization is much easier than with collinearity. And the way to understand this, or at least the way I understand it, is well, here, when you optimize, and sorry, I should explain what this picture is represent actually. So this is those lines here of constant numbers. They represent values of two betas for two predictors that have a constant RSS, residual sum of square. So all the points here, so all the combinations of beta values for this variable age and this variable limit have the same RSS of 21.8. Okay, and this smaller circle, now you have a better RSS. Obviously, you try to minimize the RSS, and then the optimal solution would be at the very center. This would be the RSS that is the minimum. Okay, I don't know what value it would be, maybe 21 or something like that. Okay, the smallest RSS. Now, the point is here, optimization is easy because when you optimize, usually you go in small increments, right? So you're trying to find the best solution. And so if you're here, you're going to move in some direction by a small increment, and you're going to see, okay, am I getting closer to the solution? And the answer is yes. Here, then from here, you're going to go here, and am I getting close to the solution? Yes. Okay, if you make a mistake and you go there, okay, not the end of the world. You're going to try a different solution, a different direction, and then you're going to eventually get to a circle that is smaller in RSS, and you're going to basically get to the solution quite easily. And wherever you are, when you do that, you should get to the solution in small steps. Here, it would be much harder to get to the solution because basically, imagine you're here and I take a small step. I need to be extremely lucky to go in the right direction that's gonna decrease the RSS, because here there's really only a specific, very tiny way in which I can improve my RSS. And I mean, yeah, because those circle of equal RSS are so narrow, right? So at least that's the way I would understand this picture. Okay, much harder to get to the right solution in this case. Yeah, and so I don't know if I have anything else to say about this. I don't think so. Okay, now I suppose in terms of terminology, collinearity would be when two predictors are strongly linearly associated. Here we distinguish this from the concept of multicollinearity, which would be when a combination, a linear combination of many predictors is strongly correlated with one predictor. How do we judge this? Usually it's using this so-called variance inflation factor. Okay, so this is what I said. A given predictor can be a linear function of several other predictors. So basically, you could have a certain predictor, here for simplicity, let's say it's x1. That is, some linear function could have an intercept, but then some linear function of all the others, beta 1 x2, then you have a second predictor would be x3, and so on, right? So it's not really that one is correlated with the other, is that this one is a linear function of several of them. And to judge this, to compute, to say, do we have multicollinearity, we compute this variance inflation factor. What is it? Okay, it's 1 over 1 minus this r squared notation, strange notation here, xj bar x minus j. What does this mean? It's not that complicated. This r squared here is the r squared that you obtain if you fit a linear regression model, but where the response is xj, and the predictors are all the other predictors that are not xj. Okay, so again, this is the r squared you obtain if you fit, as I done here. Let me just change the notation to make it consistent. You fit xj as the response, and then all the other predictors, x2, x3, blah, blah, all the predictors except xj, you use them as, well, as your predictors in this linear regression. And you see, if this r squared is very high, close to 1, it means you have multicollinearity because, yes, xj is predicted linearly by all the other predictors. And now, basically, you could have used this as a judge of the variance inflation factor. Now here, I think it's a convention that we use this this VIF instead. So yeah, rule of thumb, if it's large, then xj is considered to be problematic because it's multicollinear with the other predictors. Well, yes, because imagine this is large, close to 1, then this whole thing will be close to 0, then this whole thing will be big. And again, here, I don't think there's a magical number, but common rules of thumbs that are used, if this is bigger than 5, you might have some problems. If it's bigger than 10, that's a more maybe stringent rule of thumb. Yeah, and so and in practice, so you can compute this. It's not, I mean, there's R packages that do this, or you can do this manually. You compute the variance inflation factor for all the variables, and if you get some high values, then you consider, okay, you can refit the models by removing those predictors, and if and you might see that you have improved your standard errors, meaning that the standard errors of your coefficients might diminish then, which is good. It's good to have smaller standard errors for your predictors. Okay, an example here to bring this point home, that multicollinearity can be a problem. And in fact, I mean, here would be just collinearity, right? Because you only have 2 predictors. But I don't think I'm going to be pedantic about the terms collinearity and multicollinearity. Okay, so what is this example? Basically, you have y is a function of 2 predictors, but here we impose the very stringent assumption of perfect collinearity, that x2 is in fact 2x1. So x2 and x1, they capture the same information because x2 is just twice x1. What happens when you do that? Well, in fact, you can visualize your data that is now, aside a bit of noise, it's perfectly on a straight line. So in general, if you have y, a linear function of 2 predictors, you should see that the data is on a plane. But here, because you have in some sense lost one dimension because x2 is just a function of x1, a linear function of x1, now your data is on a almost perfect straight line. And you can see that this is a problem because what a multiple linear regression is doing, if you have 2 predictors, is fitting a plane to this data. And now here, okay, you can fit a plane, but you see, there's an infinity of planes that will fit points that are on a straight line in 3 dimensions. There's an infinity of planes that will fit exactly the line. Maybe I can go to the animation on the website. Might be slightly clearer to do that then. Let me find it. I need to share something different. The website here, because as you know on the website, those things are animated quite conveniently for you. So yeah, so here, I mean, you can move around and you'll see this is data for a y predicted with 2x's, but those x's are collinear. And then you see that the data is almost perfectly on a straight line. So if you fit a plane, you can do that. But again, the point is, imagine in your mind that I have the same data in my line, I fitted a plane to it, but then I rotate my plane. Those planes are vastly different to each other, yet all of them fit this data extremely well. Because yes, the data points sit on an infinity of planes in the 3-dimensional space. Okay, so again, this is a problem because then which of the planes is the correct one? Well, how can you choose what the betas are of your model and the betas generate a plane? Well, you can't really. So you're going to get extremely large standard errors when you fit this in R, or even R is going to give you errors when you try to do that. Okay, back to the slides. Yeah, my biggest fear in life is not sharing the right thing and then realizing later, and I need to re-record. I mean, I kind of like recording, but I have other things to do, you know, things to see, people to hang out with. All right. Yeah. Okay. So this is then the results from fitting this exact example in R. So we generate data points following this model. For this to work, for this to R not to generate errors, we actually need to give a little noise to the X2. So it's really the same thing, but we need to give a small error. Otherwise, linear regression will just not fit. It will give you errors because again of this problem of the matrix is not invertible. But what happens here? You see the outputs are kind of crazy because look at your estimates. It's like the beta one is like 5,000 no 50,000. That's crazy. Okay, but the standard error is also it's enormous, 30,000. Okay, same thing, minus 30,000, enormous standard errors. And basically here, this table tells you, okay, apparently those coefficients are not significant, which is strange because obviously the correct model is exactly a linear model in which the betas are significant, of course. So what's happening here? Well, you have run into collinearity, and here, I mean, it's an absolutely extreme example. So the variance inflation factor is just just crazy, right? I don't know how many billions that is. Okay, no point figuring. I mean, now that I've tried, so how many billions? Okay, this is 360 billions. That's crazy. So yeah, so here basically you cannot use this model at all. What would be the solution here? As I said before, obviously just drop this one. If you drop this one, you're gonna get the same R squared, but that, by the way, here is extremely big. Yes, the R squared is still very big, even though you don't have significant, apparently significant variables in your model because, well, you're still explaining, you know, your points are still on your model, right? It's just that you don't know which plane to choose. So here, your prediction might be very actually, your predictions. Well, you won't know how to predict a point that doesn't have a typical value for x1, x2, right? The prediction will depend highly on which plane you fit to your data. But if you remove one variable, then your R square will almost not decrease, and you will have a perfectly sound model here. Okay, is it the end of this topic? Yes. So bear with me, one last topic, which is called here confounding effects. And maybe this potential issue with linear regression is a little bit different because it doesn't really have to do with assumptions of the model not being respected, but it's still important to mention, I believe. In a sentence, here we just want to remind you that correlation does not imply causality. So in the case of linear regression, if a predictor X is even strongly significant in modeling a response Y via linear regression, it does not necessarily mean that X causes Y. Not necessarily. Now, it could be that X causes Y. Absolutely, it could be, but not necessarily. And more specifically here, we're going to describe one potential situation where you have strong predictors that are not really causing the response. And it's this concept of a confounder, also known as confounding variable. So C is a confounder of the relation between X and Y if C influences X, and then C influences Y. And then if that's the case, in some sense, you could have C that causes X literally and C causes Y literally. And then you will have a correlation between X and Y. So there's a relationship between X and Y, but it really doesn't mean that X causes Y, at least not directly. Let me see if I can give you an example. Well, I think it's an example I've used before in the class, but yeah, let's say that C represents some measure of if a student is diligent. Okay, diligent student. Okay, and then X is the if the student, such as yourself, watches a lecture, so minutes of recordings watched by the student, right? And Y is the result in final exam, right? So you see, if the student is diligent, well, they will have lots of minutes watched of my recordings, and then they will also have a good result in the final exam because they are diligent. Now, if I were to ignore this, or basically I don't have a valid measure of how diligent the student is really, all I have is a proxy here, the number of minutes watched. I might find a strong correlation between the number of minutes watched and the result in the final exam. It's not really, it could be that watching the recordings helps you to do a good result, but not necessarily. It could just be that, okay, diligent students tend to do a whole bunch of things, like they study a lot, maybe they go to consultation or something like that, or they ask ChatGPT to help them understand concept. And among other things, they watch the lectures, right? But it's not really watching the lectures that makes them have a good result in the final exam. It's all those other things. It's overall the fact that they're diligent, you see? But if I ignore this, or I don't have a good measure of it, and I just simply compute this, I'll see a correlation between those things. Okay, other example here. Yeah, okay. Age of a child, that would be X, would be correlated with their aptitude for mathematics. Why? In a sort of overall matter, right? If you have a set math test, say, and you give it to a 6-year-old and you give it to a 12-year-old, well, on average, a 12-year-old is going to do much, much better, right? I mean, you might say that's not fair because I'm giving the same test to a 6-year-old and a 12-year-old, but that's the point of the example, right? Overall, age of a child, yes, would be correlated with aptitude for mathematics. But the point here is that age alone does not causes a child to be better in mathematics. It's not age here that causes a child to be good in mathematics. It's more that, well, there's a confounding variable, something like overall time studying over all the years that the child is in school, okay, overall time studying. Well, this correlates, or even in some sense causes age, right? The longer you stay in school, well, the older you will be, okay? So time studying causes age. Now, time studying causes aptitude for mathematics. Well, yes, the more you study on average, the more you will be good at mathematics. So then you see, time studying is our confounder. Okay, so time studying is our confounding called C before, and then X and Y were the variables we actually observe or measure. So here the point is, if time studying cannot be measured, because yes, it's a bit harder to measure how much time a kid has spent studying. Well, age is a reasonable proxy, But obviously, it's not perfect. And you can imagine extreme cases like imagine a child you found in the jungle, okay? Like Mowgli, maybe from the, how was it called? The book, I forget the name. Book of the Jungle or something like that. Anyway, yeah, you find a child in the jungle. Yeah, they're not going to be good at mathematics, even if they're all on the older end, right? Or just a child that for some reason just never studies is just, uh, you cannot force him to study. Well, then they're not going to be good at math just because they're older, of course. Now, how to correct this? I don't think there's an easy answer. Obviously, if a confounding variable is observable, well, that's the one you should use. Okay, if the variable that literally creates the response is observable, then add it to your model. Um, if it's not available, then I suppose you need to be careful with interpretation. Well, in the presence of a confounder, you need to know that action taken on the predictor and the predictor alone will have no effect. Okay, in the simple example from before, this would be incorrect interpretation, right? Let's say that you found a correlation between age and aptitude in mathematics, and then you say, well, no point sending our kid in school, they will just grow old and automatically become good at maths. Obviously, that would be totally incorrect. Um, and yes, I'm already at the end of those slides. There's a few bullet points here about what's next. Yeah. Well, I suppose the point is that many methods we see in the next few weeks are actually very related to linear regression because they in some sense, generalize or expand the scope of linear regression. That's going to be the case for classification problems. More generally, the generalized linear models. We're going to talk about splines and generalized additive models, ridge regression, and lasso. But all that good stuff is for a bit later. For now, I hope you will spend time studying linear regression. Okay, so thanks so much for listening as usual, and I'll catch you in the next video, hopefully. Bye for now.